First and foremost, the students who have really helped me shape these ideas. Let me see, just a second. Are the Ajanta and Shingshu, Shinzen, Pradeep Nair, and Reza Satpur. As you know, that working with the students is the deepest pleasure of being a professor. And this is something, and they essentially help shape the ideas as much as my own contributions are. So very briefly, we all know that there is an explosion of electronic devices in all aspects, and then very soon there will be hundreds of billions of microcontrollers and various types of integrated circuit everywhere. This is primarily because for a long period of time we were primarily focused on computing and communication, but increasingly electronics is being asked, or electronic engineers or material scientists and all, they are being asked to address a broader range of fundamental questions about sustainability. And that may mean purer drinking water, that may mean healthcare, that may mean energy needs. And so therefore, on all these areas, we would need electronics to make them smarter, make the utilization of the resources better. And in order to do so, the electronics is going through a fundamental transformation. And the transformation, simply put, is the following: that electronics used to be, still are in many cases in data centers and all, in a well-controlled environment. In the well-controlled environment of temperature, you can essentially say what the performance are, what the reliability would be if there's some sensors not working or some transistor or board not working, you can quickly replace them. And similarly, one can develop technologies in the lab or in the temperature controlled environment where technicians, like our blood samples and all, technicians can um, uh, reliably sense them. They have a lot of training and they can calibrate the sensors and all. Increasingly, that's no longer possible because if these are Elon Musk's satellites, there are hundreds of them being launched. India is also launching a few, and then soon will probably they will also be launching quite a bit as a commercial deployer. There are solar cells in the desert environment, in the snow-covered places. So, and similarly in the smart electronics, we need anytime we talk about deployable, implantable electronics, we mean sensors that are not in the lab but in the field. And here, the life is actually very different because temperature cannot be controlled, humidity, illumination, nothing can be controlled. And once you deploy it, you can put a battery in the beginning, but the battery will soon run out. So you have to think about that issue, that about how to address the battery problem. So this is the set of topics I want to talk about. But I want to talk about not by just giving you one or two examples, but rather attacking the problem in a fundamental way. And this is just a beginning. Of course, as a community, we need to address this problem. So these are some ideas. Von Neumann is one of those giants who transformed electronics. As you all know, although Alan Turing was the person who conceptualized computers, but the person who actually built it is von Neumann. Von Neumann wrote two papers. One is very well known, that how to make a computer, and anytime you hear post von Neumann architectures, memory in logic in memory compute, near memory compute, all those things are essentially reference to this first paper, this 1943 or 44 paper. The other paper, however, is much less known. He gave it five talks at Caltech in, I think, 1948, but these were later on published as a small paper, as a paper in 1953 or so, and where he said that in building the computers, he immediately realized that completely reliable systems are fundamentally impossible because you may have a set of transistors, even if you have, let's say, 5,000 vacuum tubes, sooner or later one vacuum tube will break, and you have no idea when you multiply 3 multiplied by 8. The answer, if the computer says is 25, you have no way of knowing. Of course, 3 multiplied by 8, you know. But in a more complicated calculation, you have no way of knowing that what the output should be. And sometimes if the data itself is wrong, for example, the punch did not go through, and so the data 3 was not 3. And you would not know from the output that 3 is not 3. So therefore, there is this being real components, electronic components, all components will always be unreliable. And so in this one, he essentially put forward the idea of reliable computers with unreliable components. And his point was this, that our present treatment of error in the computer is unsatisfactory and ad hoc. It is the author's conviction, von Neumann's, voiced over many years that error should be treated by thermodynamic methods and be the subject of a thermodynamic theory as information has been by the work of Sliggard and Shannon. So this is what I'm going to do today. I mean, it's not going to be complicated. It's going to be very, very simple. But the errors has to be a part of performance, and how to overcome it has to be as fundamental as the performance is. That's what I would like to do today. So in order to do that, I'm going to invoke two fundamental concepts that we have discovered over the years. And this is nothing new. You all know all this, except that you may be just hearing it from a new context. That's it. This is no rocket science here. So concept number one is that all electronic devices has a fingerprint or a heartbeat. For example, if you have a dishwasher, in the pre-wash cycle, the one motor turns on, and then during the wash cycle, it for a longer period of time, another motor turns on, or maybe the same motor, and then in the rinse cycle, there is a lot of oscillations and all. If you knew what this individual thing does, and because you are doing it every morning you may be turning on the dishwasher. So in that case, just by tracking this signal over time. So here the sun is giving you the clock. And by looking at this signal over a period of time, you may be able to say long before the motor dies that if this one keeps going down, that motor is about to fail. And same for the washing machine and for any electronic device, you essentially have a heartbeat or electronic signature. No surprise because different components draws different amount of power. Same for an integrated circuit. In an integrated circuit, if you look at the current in the power pin or in the ground pin, it will consume powers depending on the input patterns it has. So there is a fingerprint based on the data it's processing. So that's one, principle number one. Principle number two is that all electronic devices in principle can be described by a information communication channel theory. For example, a sensor is a device that senses some analyte and gives you an electrical signal, but you can view the analyte as a message. This is a message a sender is trying to send you. Maybe the earth is trying to send you this information in the form of nitrate concentration in the soil, and you receive a voltage signal. And this is being distorted because this is in a fluctuating temperature environment, or the humidity is not good, or maybe the bacteria is eating some of the polymers in the sensor, so this signal getting distorted. You can view this as a communication channel. As soon as you view it as a communication channel, all electronic devices, whether it's a transistor, sensors, photodiodes, anything, then you have the whole machinery of the modern communication theory at your disposal. For example, if you can multiple sample something and reconstruct it back. I'm going to give you an example. But these two ideas, periodicity and communication over a noisy channel, these two principles I'm going to show you by three examples that how it can transform the way we view electronic devices. By the way, all electronic devices are sensors. because a transistor is a charge sensor, a photodiode is a light sensor, and a solar cell is a light sensor, because any electronic devices in some way must sense something in order to process that thing and give us an output. So I'll give you three examples. I'll start by heartbeat of a solar farm. This is a topic I started from, but that maybe the more interest to this audience would be the biosensors and how we have rethought about biosensing in this modern context. But let me start with the solar farm. So what is this? It will use the first principle, that periodicity, and how it can help you get the reliable signals from this system. But both principles will be in use in the biosensors context. So one of the greatest example of field deployed electronics is solar farms. Solar farms, even when I was in Madras, there they have been installing one of the largest solar farms there. Solar farms are now everywhere, miles and miles of solar farms, millions of them. Now the problem is that this one is being deployed not in our inside a room. It is being deployed it may be in Alaska versus Arizona, or in Madras and other places in the Middle East. There's no telling that what type of environment this will be installed in. And of course, in the beginning, we do a lot of work on solar cells. We can predict that on day one, that what the potential outcome would be. This is what the bidders of the farms, that's what they are going to bid on. They'll say, okay, this area looks like a very sunny, so this is going to give us this amount of energy. So they do a very good job. But after a bit, once the whole system begin to degrade over time, the only way people can analyze this type of thing is essentially take one sample out, test it in the lab, and this is the artificial sun. This is the solar simulator, and see how bad or how good it is. But how do you then monitor these millions of solar farms? You cannot just do samples like this to get a general idea about what's going on. You need a much more nuanced approach. So this is where this idea about heartbeat comes in. You see, if you were in 14th century, when people still used to think that there are five chambers in the heart, because people used to do dissection, but they used to follow the Greek text. So in that time, if somebody gave you this measurement of the EKG signal, you would not be able to say anything because you don't have a mechanistic understanding of the heart. But once you have a mechanistic understanding of the heart, that what is the mechanics, what is the physics, how many chambers do you really have, what does heart do, then every little blips and bounces, everything a heart specialist would be able to read, and thereby will be able to say this is the problem. And therefore, and this happens because you can measure many of them. For a solar farm, this periodicity will be once a day. But in here, every heartbeat gives you the peak. And by analyzing this peak, you can construct a high resolution. This is a signal processing part. High resolution uh, response of a unit signal, and thereby say what type of problem you have, and thereby prescribe some medication. People would not generally take the heart out and send it to the lab in order every time somebody goes to the doctor that I'm having a heart chest pain or something, they don't take it out. So the main thing is here, the heart is where it is. The solar module likewise should be where it is already. We should only look at the EKG of the solar module, and thereby essentially do the prescription, what to do about the solar, when should we replace it, what treatment does it need, and next time I buy a solar module, what type of solar module should I buy, given that in this environment, this degradation is happening. So these are all experimental data. By the way, fortunately, we have worldwide collaboration because some of the ideas are very new and people are finding it very useful. So for example, these are the input. This is a solar module. Remember that big farm. This is one of those modules. You have the input. This is the sun. Sun in the morning, very low, going up in the noon and then falling. Some days there are a lot of clouds. Some other day there is full of clouds and all. This is cloud moving in and out. So yes, therefore you have a pattern of sunlight incident on this. Of course, the temperature goes up and down. Summer and winter, every time the ambient temperature, you'll have this, and relative humidity. Where do you get all this information? You get all this information from the satellite and the weather station. I do not know to what extent you understand that. Probably many of you know that India has launched a set of satellites, and these data are all open. And the precision of some of the modern satellites data in terms of where you are, whether you are doing smart agriculture or solar farms or biosensing, in each case, these informations are openly available. Okay, so these are the input. And what is my output? Output is the heartbeat of the solar farm. So heartbeat, by that I mean there is the maximum power point, meaning the voltage of the module goes up and then down, goes up and down. And then similarly, the photocurrent that goes up and down and up and down, because in the noon time there's maximum light, so you get a lot of current out. And the multiplication of these two gives you the power output. And so this is what you see, the oscillation of the power output. Of course, in this day, the power output was fluctuating. So this is your input and this is your output. And this is sort of quote unquote your heart. And you have we know the physics of the solar modules, p-n junction connected in a particular way. So we know that physics very well. Given that we know that, so we should be able to say how the heart, quote unquote, is degrading over time, and we'll be able to infer its present state of condition on any given day, because this is taken at every second in a solar farm. This heartbeat is recorded at every second. So generally, remember I said that from the farm, people used to take one module out and then test it in a environment like this. This is the solar simulator like that. Remember the LED like structure, and what they used to do is that in the controlled illumination and temperature, they used to say how it is responding. And it is like taking your heart out and checking it out, that how it is pumping in various chambers, and you get IV characteristics. The thing is that you don't need to do this, because nature is every day is doing it for you. There's no reason to bring it in the lab. The reason is that nature in the morning to noon, morning to mid-morning to noon, and then back again in the afternoon, this is already doing an experiment on this phase space, which is S and T, that every time there is a illumination, there is a temperature. So if you know this S and T in this space, and if you know the physics model, you will be able to reconstruct whatever these people can do by taking things out. You can do it in the field. You don't have to detach a single one. And you can, mile after mile of solar farms, you can essentially you'll be able to see how the system is doing. So basic idea is this, that this is the unknown system, but this is a physics based system. So I already know this is my input. Input meaning illumination, temperature, humidity. This is my input. Output is my VMP, IMP, and this is why it's called Sun's VMP method. And what you have is time is your friend, because instead of doing a single point measurement, you are doing this measurement all the time, every day. And so therefore you have a lot of data that allows you to do something that you cannot do in the lab. All right. How would I do this? Many people these days have started working with this machine learning. And I don't like machine learning generally when you don't have any other approach, meaning that like image classification, we do not have a mechanistic equations for our eyes or how our eyes classify. So machine learning is appropriate. But we know how, as an electrical engineer or material science, we know how a diode works. So there's no reason to accept blindly a machine learning thing. We can just take this one. And we have all this input data if we adjust the parameters such that this input reduces, creates this output, then that will give me the instantaneous state of this solar module. For example, if the module has developed a lot of defects in the system, then this recombination current will go up. If the encapsulants, if they have become yellow because of the UV, this one will go down. So by just connecting these two and interpreting this parameter, here you may have 15 parameters, but here in a given over a 2-3 days period, you may have 10,000 data points. So therefore, you can easily fit this data. And once you do that, what you will find that how over time things are degrading. Now, things will degrade in Madras differently from Arizona, from Alaska. And their components, J01, J02, all these components will degrade differently. And that will allow you to say that given a location, same solar module, given a location, how would the module degrade and how should you design the module so that this is robust against that local environment. So this is very important when you have systems that are out there in terms of field deployed, as I said, field deployed electronics, not the comfort in the of the air conditioned room or anything. So here you can predict how things would be. Now we have worked with a lot of people. By the way, these codes are all available in GitHub. And so therefore you can take a look at the code. So this is your input. These input are all coming from the satellites. The codes have direct API to the satellite so that you get the satellite data. Generally, we have about 40 years of historical data and as well as new data coming in every day. And then at every location, two kilometer by 2 kilometer grid across the whole world. And this is the response of your solar farm. Whether if it's in Arizona, it will have one value. If it is in Bombay, it will have another value because the sunlight will be different, the temperature, local temperature would be different, and so on. And so therefore, this system will degrade in a different way. This idea that given the input environmental conditions and looking at the heartbeat, that you can extract the equivalent circuit inside physics-based is a general idea. Yes, here it's for solar farms, but nobody prevents us from doing it for a biosensors, and that's what I'm going to show. That once you have deployed it, you can monitor it to see without taking it out or doing anything that how the sensor is degrading over time, and therefore what you need to do when you do next generation of solar modules for India, for example, versus Saudi Arabia versus some other country, or when you deploy something in one location versus another, depending on the soil quality, you'll deploy it and design it differently. So I am just plotting the various components that how things are degrading, and this is the summary of it. How is this a 20-year period? This is taken from Sandia National Lab, just as an illustrative example, and you can see series resistance degrading very quickly. In this J02 or this photocurrent, this is because of the yellowing, because we know the physics of when photocurrent degrades, what happens in a solar module. So therefore, we can connect this degradation with the corresponding physics, just like a heart specialist will see the signal and will be able to say, okay, this valve or that artery is not behaving properly. So let me give you an example that how that connection happens. For example, the series resistance. Let me explain that in this location looks like the series resistance is killing the solar farm. And how do you know which part of the solar module is connected to the series resistance? So let me explain that in a few minutes. So I'm not sure whether all of you know about solar modules. It's a beautiful piece of physics, physical device. Someday, maybe if you don't know, you'll take a look. But very briefly, the idea is that in the solar, it's the top view, and there are lots of fingers in here, very thin. You can probably barely see them. And then there is a bus bar. So this you can like a local road, and this is like the highway between interstate highway. So generally, if you want to go from your home to some other city, you will take this photocurrent will take this path through the finger and it will go here. Assume that one of the days, one of the entry ramp or exit ramp are broken. So if it's broken, then you have to take a longer path through the bus bar, and therefore there will be an additional resistance because you are going through. It will take longer. It will be more resistive. So anytime you have this solder bond breakage, then typically you will also have, this is reflected in the IV characteristics. By the way, this is the heartbeat. So as you have more and more of these things broken, then you will have this resistance, the slope of the curve will gradually increase. And was the hypothesis. We did a huge amount of experiments, about 500 samples, to correlate directly that the physics of series resistance increase is always and always correlated to solder bond failure. So these are the sort of the number of hotspots, meaning number of broken. So there are about thousands of them in each module. So anytime something breaks, it hits up because there's more resistance, and therefore you can correlate it with the resistance that you have measured. And because you now know that every time there is an increase in the series resistance, that means these things are broken in any location in the world. Any location in the world, if you see series resistance increasing, then you know that the modules that you have bought for your or for the company that you have worked with, that company needs to put additional tabs because otherwise this is not going to survive in your local environment. Right? This is the doctor's prescription part. That so these connections we have established. For example, I'll just give you one or two examples. These are from America. In America, generally you have series resistance drop, but you also have potential induced degradation, you have corrosion, or spelling is wrong. You have significant amount of corrosion for these particular locations in Sandia, and this is in Denver, Sandia and Denver. But you can see that this is in the Middle East. In the Middle East, primarily failure is solder bond. You don't have to worry about other things. So you can see because the Middle East has a very different MENA region environment, and so therefore it has very different failure characteristics. And this is something we are also trying to do for India, Bangladesh, and other places because we have a theory about how things will degrade, and we have this data. From the data, we can do this comparison that whether the theoretical predictions about how things will die in the field are similar or different from what the field data tells you. So this is purely from the field data by reinterpreting the heartbeats, and this is for a theoretical prediction that what it could be. And then, of course, as you get more and more data, you can just essentially compare at every location in the world. So we have worldwide collaborations, a lot of group work with us. All right, so let me get to the second part. The second part is about beautiful pictures and difficulty in reproducing the results. So these days, one of the things I find it mildly amusing is that people have learned, especially in the biosensor area, people have learned how to draw beautiful pictures. And the beautiful pictures, of course, involve a lot of sensors. They all work flawlessly, and the results are shown and discussions are done. It seems like that in the next year, there'll be a commercial product. But I know that except for the diabetes sensor and maybe for pregnancy test and a few other things, essentially there are very, very few wearable devices that are in the market. Why not? Why doesn't all these beautiful pictures and thousands of papers transform the field? While in transistors area, they wrote 5, 6 papers and in the beginning, and that transformed the field, started in industry. Why doesn't it happen? This does not happen, and I'm going to explain to you very simply that what's the trouble. The trouble, and I'll give you the example through ion selective sensors. So ion selective sensors is essentially is a very simple sensors. People have known it for 100 years. And the basic idea is the Nernst equation. The Nernst equation says that if you have two electrodes and put it in an unknown solution, and that unknown solution then, and if you have a ion selective membrane, then the ion, let's say sodium chloride, you want to determine sodium chloride concentration, then sodium goes in, but chlorine cannot. So it forms a p-n junction, just like a solar cell, no different, same physics. That's why biosensors, and that's a fundamentally same physics, same equation. And so the idea is that you go to the lab, the technician will set the T, and then they will calibrate every morning. If the calibration curve is not working, they will throw that electrode out, put another in, and then they will measure psi, and they will say, well, this is the concentration of sodium in your blood or potassium in your blood. You know, you get the blood report every time you go to the doctor. And of course, these are used in wide variety of cases in fisheries, in blood testing and all. This is, but there, what we don't realize that this is all temperature and not are controlled. In all these things, this is the same control. But people who are not sensitive to this fact, what they will say, oh, I can make a sensor very easy. I can make a flexible sensor and I can put it in a roll to roll and it will be very cheap. These people don't know anything. Why are they making this complicated instrument? I can do it in 10 cents and deploy it, and I will deploy it in here. But the rude awakening happens relatively quickly. The rude awakening is that once you don't have these two controls, then you measure psi. But is the change in psi because of the temperature, because bacteria ate the polymer, or because of the change in the concentration? You have no idea. And so therefore, you cannot really do anything. So as soon as you put the data in, then you cannot really, this is completely unusable. Now you can say, I could put a thermometer. Yes, that's possible. You can put a thermometer inside. But are you going to put a thermometer on each one of them? And then if you put a thermometer, the amount of power it will consume, any battery that you put in will die in maybe 1 month at most. Any battery that you put in. And the cost of the battery will be much more than the sensor itself, the 10-cent sensor that you said that you will make, it will be actually much more. This is the reason why this nothing really makes it to the, I shouldn't say nothing. It's difficult to break a, even the diabetes sensors and other things, those are in our home in a typically comfortable and temperature controlled environment, and generally it's expensive. So what do you do? In fact, it turns out it's even more horrible. When I started working on this, I thought I'll get beautiful data and I will just work on it. The students started complaining that this is what they saw. In a given day, so this is a large field and there are multiple sensors have been placed, and these sensors are measuring things. So therefore, there is a water coming in and you are measuring the nitrate in the water. Why nitrate? Because as you know that people are using too much fertilizer in most of the world, too much fertilizer because they want a short-term gain in the, and if they see at one point that the nitrate concentration is low, they put fertilizers everywhere over the big field indiscriminately. So if you could locally measure with low-cost sensors on a finer scale, then you could tailor the additional nitrate concentration. When nitrate goes to water, that essentially kills all the fish, makes water undrinkable. So that's why you want to have a lot of sensors distributed, but this is what you get. This is we spend a lot of time creating this structure, but at the end got horrible signals, and the signals is fluctuating all over the place. One sensor does one thing, another sensor does another thing, and you cannot just choose one and publish a paper because all the sensors are what it is. And when you bring them to the lab, these are the things that you get. Bring them in the lab in the temperature controlled environment and measure the nitrate concentration of this water. This is what you get. So therefore, how are you going to even get anything out? And then think about it. Initially, it was one thing, and then it is drifting. So how is it possible to get anything out of this system is the challenge that we had. So I mentioned to you that communication system theory can be helpful, and I'm going to give you some example. The main point is, the main point here is that time is your friend. That is the essence of a communication theory. That when you have a noisy channel, you can send the signal multiple times, or you can speak loudly so that the other person can hear you. So there are many techniques. The main important point is instead of a single point detection, you have continuous measurement. And anytime you have continuous measurement, you can do things that you could not have done if you had a single point lab type measurement. So this is the additional thing you have in the field that you do not have in the lab or in general context. So let me give you an example how it works. Strategy one: how a sensor can it becomes its own thermometer. It turns out that if you look at the physics, if you have two sensors, generally, we always want to make the sensors uh, as uniform as possible. But unfortunately, in our system, it was a roll-to-roll system. So we could the uniformity is whatever it was, we could not change it. So it turned out that what I said that okay, if the uniformity cannot be changed, if it cannot be made any more uniform, can we do something where the non-uniformity becomes a resource? Just like time is a resource, can non-uniformity become a resource? And you see how it happens that if you measure on one of these sensors, this is the sensor, what it's doing in the field. Psi1 is KT over Q, but because these sensors may have a slightly different thickness, this N01 and N02 are slightly different. So therefore, they are giving you two different signals. The great thing about it is that if you take the difference, this N cancels because it's a log. The N cancels, and if your N01 and N02 are constant for a second, just temperature is fluctuating, then you can see by measuring delta psi, you can measure T. And if you can measure T, then if the T known, you can get N from the psi, you can get an N. So you solve the thermometer problem, and this is zero energy thermometer. This is a nurse thermometer. It's not a resistive thermometer. So it doesn't consume any energy at all. And you can still measure temperature. And this is how you measure the temperature. You see just the difference. So two imperfect sensors, S1 and S2, together makes a perfect sensor. This comes from communication theory that if you have one channel versus two, then you can essentially send the signal better. So this I will go through quickly. So these are all field data, four sensors. You subtract pairwise and you get the temperature. By the way, if any of your sensor is degrading, N01 and N02 is not correct, then what will happen? That pairwise difference, the temperature will not agree. And that is a signature that your sensors are degrading because over time the polymer may be sort of decomposing. So the temperature is not only a thermometer, but this is also your degradation monitor. When you have pairwise, let's say you have three, one of them is degrading. So these two difference versus these two difference versus that difference will essentially will not agree. And when the one that does not agree, immediately you know that that one is degrading. So by the way, so if it does, you have that information, and once you have that information, all these signatures essentially goes away, and because you can correct for the temperature. These sensors are degrading, so therefore you cannot really determine from use that information, but you can use this information to find out what's happening in the sensor itself and how the concentration is changing over time. So let me not go through all the details about how we went through. This is an extensive 4-year long program where we try to create the foundation. And at the end of the day, this is what the lab measurements were, the red ones, and this algorithm of how to use the differential temperature as a thermometer as well as a degradation monitor allowed us to sort of get the true signal even from the noisy, horrible thing which had no meaning in the beginning, essentially allowed us to extract this information. So what is it that helped us? One is time, because we had a lot of signals, so therefore we can take a difference. Second is that N does not change as frequently as T does. So that was another thing that helped. And the third and most important thing is redundancy, that we had three or four instead of one sensor. With one, you cannot do anything. I'll give you an analogy, and I'll stop with that. Not stop. I meaning close this topic. The analogy is that, if you, let's say you have multiple clocks, cheap clocks in your home, and you have a reference clock. And so every day you let it run. In the beginning, everything is the same. But after 1 year, let's say, or after 6 months, whenever you check, they are not all synchronized. Then you go and synchronize them. Then you can make the sensors good again. So that's the approach we used here to extract the information that we needed. All right. But it turns out that sometimes you not know the physics. Here I knew the physics, Nernst equation, solar cell, I had the compact model. If you don't know the physics, then can you do something? Of course, you can do a lot of things because the modern Facebook, we often complain about Facebook and Twitter and other things. The students are spending a lot of time, or professors maybe even spending even more time. I don't know. But it turns out that the algorithm that are underneath those new platforms are foundational algorithms. And I want to show how to use some of those algorithms to change the way we do biosensing or any sensing. And this is the idea. When Facebook tries to detect a fake news, it doesn't have a ground truth. Let's say something has happened in Bangladesh, in Dhaka, and 10 people are posting on their social media posts that this has happened. Now, one of the person may be a social media influencer, and that person may not even have gone to the location, still writing something. The other people at various degrees of credibility, they are sort of posting. How do you get the real news from this collection of newses? Again, redundancy. How do you do that? So here is an example. Assume that these dashed lines are your true news. This dashed line. The news could be nitrate concentration. News could be your state of the solar cell, but let's say this is the true news. Now, in some news organization is highly reliable. Let's say in New York Times, let's say they try to do reliably, but you don't know. You have no idea. Some news source, let's say Fox News, they may be consistently unreliable. But you do not know that who is unreliable and who is not. And some news sources, depending on the day's news, they are reliable if it favors them, not reliable when it doesn't favor them. So you have a random thing going on over here. So you have four sensors. You have no idea about the black line. So what can you do? Okay, should you just average? If you do the average, then the single one, which is horrible, will essentially distort everything. Even if you do majority voting, that will not work because sometimes the blue and the red together may outvote the reliable sensor. So it will not work. What you can do instead is what they call a Bayesian MLE. This is the technique they use in Facebook and other places in order to get the reliable signal. That you look at how consistently, because truth is one, so when people are telling the truth, like police interrogation, when people are telling the truth, they will essentially their stories will be consistent, and the person who has told the truth consistently before, chances are that person will tell little bit higher probability. So instead of giving everybody the same probability and just looking at one time, you look at the historical how reliable they have been and assign a continuously evolving credibility index. So this one, after in the beginning, everybody equally credible, red and blue and all. But after a few days, because red is always so far from other people, gradually its credibility index will be lowered and eventually it will be thrown out from voting. So this is what they use in fake news detection. So that is what we did as a part of this approach, which I did not show you, that by looking at it, I can say that this sensor, remember the biosensor which is drifting, that this is really becoming a fake news fake news generator. But I would not know a priori if I did not know the physics that this is doing. How do I know which one is fake and which one is right? And what you begin to do is using that MLE, you can essentially do the credibility index of the sensors that one and two are more credible because they keep telling the same truth and they begin to agree more with each other, while the green and the other ones are generally unreliable. So that way, that is how you get this signal out. By the way, this is exactly how a collection of bacteria detect signals below the thermodynamic limit, because individually every bacteria is walking in a tornado. Water molecule is constantly bombarding them, and this tiny creature is essentially getting randomized every second. And yet they can detect the signal where the food is just by essentially collectively averaging their signal with appropriate delays, and thereby essentially they can survive. They hunt like a wolves together. Individually, they would not survive. So, how many do I have? Or I've taken quite a bit of time. I think I should probably close. So, let me just briefly show you just a few things. I'll not explain too much in here. Another problem people generally have is the energy harvesting. And what I want to just tell you that every sensor can be used as its own energy harvester. Because when you have a microphone, you are speaking, that's good. But when somebody is not speaking, then the piezoelectric sensor can essentially also be a piezoelectric energy harvester, and thereby from the ambient noise. If you have a photodetector, when it's photodetecting, good. But it photodetects for a fraction of a time. Rest of the time, it's just sitting there. So if you have a circuit which for the rest of the time uses as a solar cell, then it can store the energy in a capacitor. And when this one needs the transmit signals or photodetector signal and all, it can use its own energy. So same for router in your home or the pH sensor. So often we have it energy challenge, because battery, if you put a battery in the sensor, the battery can die and then the sensor is dead, although the sensor could in principle sense. So what we had been trying also, and I will not get into the details, is how to harvest energy from the molecules themselves. And the only thing I would say, uh, anyway, I think I wanted to show you a result just to show you how significant from a density gradient. If you have a nitrate in one place or salt water in one place and river fresh water, from this density gradient, you can harvest a huge amount of energy. So chemical sensors can always be their own battery, and you can get almost 100 nanowatt of power. This should be nanowatt, 100 nanowatt of power in terms of from this, and only a few minutes of harvesting should be able to support communication between various sensors. I know I'm going very quick on this one, just to wrap it up. Let me not get into this other problem. This is the final topic I wanted to talk about, that sensors essentially always have corrupt data supporting sensors. So you're measuring potential, but if your temperature, you also need temperature. And the temperature sensor, if it is corrupted, then your chemical sensor cannot be used. So this is a problem again, once again, that one needs to address in the field deployed system. So let me conclude here. I think I had a few more things, but let me not get into those. Just to conclude then, I started by saying lots of electronics deployed all over the world, but this is not, we often think about FinFET and other things. That's where our research is. The research, yeah, part of it should be there, but vast amount of this treasure trove of new information is coming from the other fields. And that requires not, we cannot just take a semiconductor textbook formula or a sensor formula and then just deploy it. Because these applications, whether it's a car, whether it's a solar farms or sensors, requires a different approach. And I said that new approaches of reading a heartbeat, communication theory, and quorum sensing. Quorum sensing meaning collective decision making. This, if we could borrow, I have a great hope that these would be possible. So that's it. Let me stop here.